two techniques are predominantly used for securing the chain and for efficient validation and verification: hashing and asymmetric key encryption. These techniques depend on several complex proven algorithms. We'll provide a high-level view of the application of these algorithms and the critical role they play in securing the decentralized chain in the 4 lessons of this module, namely public key cryptography, secure hashing, transaction integrity, and block integrity. We'll begin this module by discussing the concept of asymmetric key encryption. Then we'll define the concept of hashing, followed by the algorithms used for various hashing needs of the blockchain protocol. We then explain the techniques that use these algorithms to manage the integrity of the transactions and the blocks in a blockchain. Learning outcomes of this module are to summarize the working of the public key cryptography, explain simple hashing and Merkle tree hashing, explore the application of hashing and cryptography in protecting the blockchain. Recall that blockchain's decentralized network participants are not necessarily known to each other. Credentials cannot be checked by the conventional means such as verifying who you are with your driver's license. Participants can join and leave the chain as they wish. They operate beyond the boundaries of trust. Given this context, how do you identify the peer participants? How do you authorize and authenticate the transactions? How do you detect forged or faulty transactions? We can do these things by using public key cryptography algorithm that we'll discuss in this lesson. Let's begin by examining simple symmetric key encryption. The same key is used for encryption and decryption, so it is called symmetric key. Example: Caesar encryption is the simplest one where alphabets of a message are shifted by a fixed number, and this number is called the key. In this example, f is a function defined by shift by 3 an alphabet. Consider meet me at the cinema. You shift by 3 the ASCII value of every letter to encrypt it, and your receiver decrypts it using the same 3 as the key. Shift the other way every character to view the original message. 3 is the key in this trivial example. Since the same key is used for encryption and decryption, it is a symmetric key. Note that the key and the encryption and decryption functions are typically much more complex in a real application. Note that symmetric key encryption has issues. Number 1, it is easy to derive the secret key from the encrypted data. And number 2, the key distribution. How do you pass the key to the participant transacting? These issues are further exacerbated in a blockchain decentralized network where participants are unknown to each other. Let's now examine how public key cryptography addresses these issues. Instead of a single secret key, it employs 2 different keys that take care of both the issues of symmetric key encryption. Let lowercase b, uppercase B be the private public key pair for a participant in Buffalo, New York, USA. Let lowercase k and uppercase K be the pair of keys for the participant in Kathmandu, Nepal. Public key is published, private key is kept safe and locked, typically using a passphrase, and the pair works as follows. Encrypting function holds 2 properties for the key pair. The public key private key pair has the unique quality that when a data is encrypted with a private key, it can be decrypted with the corresponding public key and vice versa. Now let's look at an example. Authenticate the sender and the receiver. We'll examine just one common use of asymmetric key encryption. Let's say a participant in Buffalo wants to transact with a participant in Kathmandu. Instead of sending just a simple message, a participant in Buffalo will send a transaction data encrypted by Buffalo's private key and then encrypted by Kathmandu's public key. Kathmandu will first decrypt the data using its own private key, then use Buffalo's public key to decrypt the signed transaction data. This ensures that only Kathmandu can decrypt and receive the data, and that only Buffalo could have sent the data. A popular implementation of public key, private key is the Rivers-Shamir-Edelman RSA algorithm. Common application of RSA is the passwordless user authentication, for example, for accessing a virtual machine on Amazon Cloud. Though RSA is very commonly used in many applications, blockchains need a more efficient and stronger algorithm. Efficiency is a critical requirement since public key pair is frequently used in many different operations in blockchain protocol. Elliptic curve cryptography, ECC family of algorithms, is used in the Bitcoin as well as in Ethereum blockchain for generating the key pair. Why ECC, not RSA? ECC is stronger than RSA for a given number of bits. Did you know that 256-bit ECC key pair is equivalent in strength to about 3072 bits of RSA key pair? Both Bitcoin and Ethereum use ECC-based algorithms for their encryption needs.